1, officially welcome everyone to 60 Minutes in Space. We're very excited to have this program tonight. We have two of our space scientists, some of our best space scientists at the Hubble Museum to present tonight, and very cool stuff. Now, during the program, if you have any questions, please put those in the chat. I will be keeping track of those. And if you're watching on YouTube, we're broadcasting to YouTube Live tonight as well. Put it in the chat there, and we will keep track of those questions. And at the end, we'll have some time to answer those questions. And with that, I'd like to introduce our Assistant Curator of Space Sciences, Dr. Kachun Yu. Take it away.
All right. Well, thank you, Mitch, for your wonderful introduction. And welcome, everyone, to 60 Minutes in Space. I'm Kachun Yu. And for this program, for those of you who are tuning in for the first time, or maybe you haven't seen us for a while and need a refresher, our program covers the latest news from the past month about science happening off of our planet. And so typically I cover topics in astronomy and astrophysics and things outside of our solar system. And my colleague, Naomi Paquette, who is an Earth and space science specialist at the museum, often takes stuff inside the solar system, including topics on planetary exploration and human spaceflight. But for tonight, Naomi will stretch her wings and also delve into topics involving things outside of our solar system. And I'm actually going to be focused strictly on black holes, and I'll be talking about both what we think is the closest black hole to us, as well as the most one of the most distant set of black holes. And so with that, definitely, as Mitch said, feel free to throw your questions into the chat, and I'll get started. And so let me go ahead and share my PowerPoint. And so what as I said, I'm going to be talking about black holes. And I just wanted to start off with just an artist's depiction of the very first black hole that was ever discovered. And black holes, as many of you know, are objects that are the end stages of very massive stars. And when these stars go supernova, much of the star gets blown off in the supernova explosion, but the inner core of the star collapses. And if it's massive enough, it collapses to a point where the gravitational potential is so strong that not even light, if it gets too close to the black hole, it will continue to fall in. And so even things traveling at the speed of light are not traveling fast enough to escape. And so that makes black holes extraordinarily difficult to observe because you can't see light from them. And for a long time, black holes were merely theoretical constructs. People had theorized that something like them could exist, but it wasn't until Cygnus X1 was discovered, the very first black hole, that astronomers realized that black holes could be observed. And in this case, the black hole was a star that was part of a binary pair. And the star collapsed into a black hole at the end of its life, but it was orbiting close enough, or its orbit evolved so that it was close enough that gas overflowed.
And Kachun, we're actually not seeing your presentation.
Oh, oh, here we go.
There it is.
Yeah, so gas overflowed from the star that still survived onto the black hole. So this is still my first slide. You haven't missed much yet. And what that gas does is it piles up into an accretion disk of gas that slowly spirals in. That gas heats up because of friction to millions of degrees, and that heated gas then emits X-ray light. And so this black hole is first observed in X-rays, and hence its name X1, Cygnus X1, meaning the first X-ray source found in the constellation of Cygnus. And then one of the other things that we know about black holes is that as part of the physics, the gas can also get expelled closer in at the edge of the accretion disk. And so many black holes that we see often have jets that come out along the polar directions of the black hole, so perpendicular to the disk. And then in this picture, you have the sun in comparison. So this is how big our sun would be. And our sun is about 100 times bigger than the Earth. And so this is a black hole that's about 22 times the mass of our sun. And oftentimes you'll see depictions of black holes like this, artistic depictions, where you see them in binary systems. And oftentimes you'll also see them depicted as emitting light from the accretion disk. And because the amount that gets secreted, or the amount of material that falls in, can be irregular, it's not a constant stream. The amount of material in the accretion disk can be lumpy, and so you might expect the emission to be transient, meaning it jumps around. So it's not steady, the light coming from the emission disk. And now one question might be if you can observe black holes when they're close enough to pull in gas from its binary companion. What happens if the black hole is further away? In this case, the black hole could be so far away that the other star, can hold on to the gaseous envelope, because its gravity would be stronger if the black hole is further away. And so here, astronomers have thought of other scenarios. So to really understand that, let's look at binary systems. And so if you have a pair of binary stars, and the two stars are about the same size, then what will happen is that the stars will orbit a common center of gravity, like we see in this video. Now, if one of the two objects is much heavier than the other, then what happens is the center of mass between the two objects is not exactly halfway in between, but if one object is a lot bigger, it can actually be inside that object. And so the two objects will still orbit it, but one of them will be just slightly displaced as it orbits, while the other object orbits much further away. And this is the scenario that we find in our solar system, where the sun is the dominant gravitational source in our solar system. So all the planets orbit around a center of mass that's inside our sun. Now, one way that you can use this to help look for, let's say, other planets around other stars, is if you can measure the velocity of stars as they're orbiting. And in cases of stars where it's moving slightly closer to you as well as moving slightly away from you, let's go ahead and replay that animation. You'll see that the star will be blue shifting or red shifting. You'll actually be able to see the light, the wavelength of the light shifting. It's towards the blue or towards the red part of the spectrum, and we can actually measure that using an instrument called a spectrograph, looking at observing the starlight. And so if you can do this if the other object is a planet, which otherwise doesn't emit its own light, and the amount of reflected light that the planet emits is very small compared to the star. Or you can imagine the other object being a black hole, which might not emit any light at all if it was far away enough from the star that it wouldn't have an accretion disk. And so this is what a group of astronomers from the University of Ohio were doing about a year and a half ago, when they released a paper announcing the first non-interacting low-mass black hole star binary system. So in this case, what they're announcing is what they think is the discovery of the first black hole system where the black hole is far away enough that it doesn't pull in gas from its binary companion. That's what the non-interacting means. And what they did was they observed the brightness of the star, and these are plots showing the brightness over time. You can see that they observed between 2014 and 2015, 2016 and 2017. and so forth. And they were able to see the brightness of the star change by very small amounts. And that was entirely due to the fact that you're seeing the distance of the star changing. And they observed this at multiple colors or wavelengths. And so you can see that you see this periodic pattern to the brightness changes from the infrared to the red to kind of the greenish part of the spectrum to the blue. And then they were also able to measure the velocity of the star. So here you can see that you're looking at velocity changes on the order of tens of kilometers per second. So, that's pretty fast, many thousands, tens of thousands of kilometers per hour. But it perfectly fits this cycle. And they were able to come up with an argument that the object that they're seeing is a black hole. So more recently, just this past month, the same group led by Todd Thompson, he's the astronomer who leads the team at Ohio State. But this paper is written by a graduate student, Thurindu Jayasinghe. And so here they announced the discovery of a black hole that they think is 3 solar masses in size. So that means it's 3 times the mass of our sun. And it's orbiting around orbiting with a red giant star called V723 Mon. And they have a clever phrase in the title of the paper. They call it a unicorn in monoceros, and that's because Mon is short for monoceros. This star, this binary, is in the constellation of monoceros, the unicorn, and of course, having a non-interacting black hole is quite a find. So that's also you can also think of it as a unicorn, a very rare thing. And so here is an artist's depiction of what this system looks like, although the sizes are really exaggerated. So the black hole is actually much, much smaller. It's actually on the size of, on the scale of a decent sized city here on Earth. So it would be far, far smaller than the star. And the star is on the order about 25 times the diameter of our sun. So the star in this case would be much, much larger. And this star, binary star pair, is about 1,500 light years away. So based on that, not only is this another non-interacting black hole, but it's also the closest one that we know of. And there have been others, other black hole candidates that have been announced in recent years. And a couple of years ago, I even talked about it in a previous 60 Minutes in Space back in 2019. But subsequent work has cast doubt on those other announcements. And so right now, unless other people come up with better observational evidence to show that these particular sets of observations have been misinterpreted, this is the closest black hole that we know of to our solar system. All right, so here is a figure from their paper showing the radial velocity. So again, this is the how fast the star is moving, and you can see they have lots of measurements, actually from 2 other sets of papers. So these radial velocity measurements weren't even by them, but they're able to show that the star moves in a manner that shows it is in a binary system with a period of about 60 days. And what the results that they basically come up with is they have the red giant star that's orbiting the black hole. It's only about, it has a mass roughly equivalent to the mass of our sun. or maybe slightly larger. And the black hole has a mass about 3 times the mass of our sun. And this is another artist depiction. So again, this isn't accurate at all, but it just gives you an idea of what this looks like. But the separation between the black hole and the star is almost about half the distance between our sun and planet Earth. So not quite half an astronomical unit. And this is what sort of a schematic of what it might look like from above. And what we're seeing on the right is the fact that tidal forces, the gravity from the black hole, is also distorting the shape of the star. And because the two masses, one star is the smaller star is only 1/3 the mass of the black hole. The center of mass that they're orbiting isn't halfway in between, but it's also not right inside or very close to the black hole. So they're both orbiting a common center of gravity, but the star is also close enough to the black hole that the tidal forces are distorting its shape. And this paper, the authors actually provide evidence to suggest from the computer fits to all the data that they have that there is some variation in the shape of the star, so that it's not quite spherical, but has this weird ellipsoidal shape that changes as the star orbits. Right, so another really interesting thing about this discovery is that we know of a lot of compact objects like neutron stars, which is another end state of massive stars, but instead of collapsing all the way, they end up being objects that are maybe about 10 miles across. And so they typically are no more than about 2.5 times the mass of our sun. And then we also know of a lot of black holes, mostly objects that are up until now have been discovered with via X-rays or other electromagnetic radiation, and they're part of binary systems. And these tend to be relatively a lot more massive, so on the order of 5 times to 20 times the mass of our sun. And then there are a bunch of other black holes that we have been discovering using gravitational waves. And so these are black holes that are the result of mergers of smaller black holes, but even the smaller black holes tend to be black holes at least 10 to 20 to 30 times and even 40 times the mass of our sun, and they merge into even larger black holes. And so if you look at all those black holes and other compact objects put together, you can see that there's kind of a gap between about 2.5 times the mass of our sun to about 5 times the mass of our sun. And so there's been kind of a mystery as to why we haven't observed any black holes, and being able to add to black holes that are about 3 times the mass of our sun, and coming up with techniques that allow us to observe black holes, that are of this size, can help us kind of fill in this gap, and also perhaps help us understand black hole evolution better, because perhaps what's going on is that as black holes evolve in systems, they gain more mass, and so you don't actually observe them until somehow they've gained enough mass that they've also managed to wander closer into orbits around their companion stars. But until we have many more black hole candidates or black holes that we've observed, we don't quite know what the evolutionary models of these smaller black holes might be. So having more examples will definitely help astronomers understand the evolution of black holes. And then since we're talking about black holes, I'd also like to talk about the black holes at the other end of the size scale, which are the supermassive black holes. And these are black holes that are in the centers of entire galaxies. So, and every galaxy that we've made careful observations of, we have observed evidence of these supermassive black holes. And these black holes can be millions to even billions of times the mass of our sun. And so we think at the centers of most, if not all, galaxies, we have these black holes. And again, there is evidence that gas is falling into accretion disks, and the gas slowly spirals in. But these accretion disks are extremely hot, and they also eject or emit jets of material that shoot out along the polar directions of the black hole. And so here are just additional artist depictions of what they look like. And even our Milky Way galaxy has a supermassive black hole at its center. So here we're zooming in to some static images of our Milky Way. The center of our galaxy is about 26,000 light years from us. And the black hole at our center is about 4 million times the mass of our sun. And so our observations show stars, very massive stars in orbit around a central object that doesn't emit any light. And so you can see here they put in a white blob where the black hole is supposed to be. And we've watched stars go through not quite a whole orbit, but what you're seeing is an animation based on what we think those orbits would be. And it's basically using the orbital dynamics that we observe from these far off stars that we can actually deduce that this black hole has a mass of about 4 million times that of our sun. And so, as I mentioned, we notice black holes in the centers of pretty much all galaxies, and that includes the most distant galaxies, the quasars. And quasars are objects that are extremely bright and they are extremely distant. And in fact, the reason that they were even noticed and observed by astronomers is because the black hole engines at their centers were so bright that they gave off this star-like glow, this point-like glow. And when they were first observed, our telescopes weren't powerful enough to see the rest of the galaxy around the black hole, the other stars, all the stars that made up the rest of the galaxy. We could only see the bright black hole engine at the very center of that galaxy. So the very first quasar that was ever observed was 3C273, and it was observed in the radial, and it was published in the radial catalog in 1959. And so here is a much more modern Hubble Space Telescope image, and you can see again that very bright core to that galaxy, again powered by the kind of the fierce furnace around that black hole. And you can even see a kind of a series of knots of a jet that's emitted coming off roughly about the 10 o'clock position. So going off towards the upper left. And so there, and then all around are other faint galaxies that are typically, I think, much closer. And so the smudges that you're seeing are more nearby galaxies. And then there's a single bright, or it's actually a dim star off to the lower right. Now, the reason why quasars are really interesting is because we think they're basically precursors to galaxies today. And they're so, because they're so far away, where the light that comes from them has taken billions of years to travel to us. So we're basically seeing the light from these galaxies and these galaxies as they were billions of years ago. But over the lifetime of the universe, these galaxies evolve. And the way that they evolve is that they merge and collide with other galaxies. So even though the universe is expanding as a result of the Big Bang, the galaxies are still attracted to each other via gravity, and over time they'll evolve and by merging and growing. And so the second paper that I want to talk about and end with is a report on the discovery of a double quasar. So a pair of quasars that we think that the astronomers think are merging. And this is a team led by Yuri Shen at the University of Illinois Urbana-Champaign and his collaborators from around the world. And they're using a technique called the astrometric technique. And briefly, the idea is that if you're observing these quasars using ground-based telescopes, if there's a double quasar, a pair of quasars that are about to merge, normally they're so close together that the bright quasar cores can't be resolved. They basically look like a single point of light. But the brightness of each quasar varies independently of each other. And that's just because each quasar has its own accretion disk around each black hole, and each accretion disk, their brightness changes because the amount of material flowing into the accretion disk and into each black hole varies and changes. And so you can expect the brightness of each quasar to change and be independent of each other. And then what happens is that if you look at the combined brightness of the unresolved black hole or of the unresolved cores, they will cause the center of that core to bounce around, or what they call jitter. And so basically what the astronomers did was they identified potential quasar pairs that were too close together to be resolved from a galaxy and quasar survey known as the Sloan Digital Sky Survey. And then they used another survey from the Gaia satellite, and the Gaia satellite mission allows astronomers to measure the positions of objects like stars and quasars very accurately. And then they looked for Gaia identified objects that had a lot of what they called astrometric noise, meaning the positions of these objects seemed to jump around quite a bit. And then they looked for objects that were relatively further away, so the objects that must be distant galaxies. And then they also use, then they finally used the Hubble Space Telescope to try and find, to see if these were in fact unresolved pairs of quasars. And so they found 15 candidates and used Hubble on 4 of them. And out of those 4, they found 2 pairs of quasars. And so here are the Hubble Space Telescope images. And you can even see that from different times that there's slight changes to their brightnesses, and so that's reflected in the red and blue composites that you're seeing here, and the distances between the quasar pairs are listed on the bottom right corners. So 3.8 kiloparsecs or 3.5 kiloparsecs. And that's roughly on the order about 10,000 light years. So that's extremely close. You have to remember that our Milky Way galaxy is about 100,000 light years across. So the separation between these 2 quasar cores is only 1/10 the size of our Milky Way. And so here is an artist's depiction of what those quasar cores might look like. But as we discover more of these, again, astronomers can use these observations to help check our models and computer simulations of how galaxies collide and merge and evolve. And so with that, I want to turn the program over to Naomi, and I'll be happy to answer questions at the end.
All right. Thank you, Kachin. We're going to start much closer to home than those supermassive black holes that Kachin was talking about. So we are still starting outside of our own solar system, as Kachin mentioned, but with our closest star in our solar system, which is Proxima Centauri, just about 4 light years away. So to give you a bit of an orientation, you can see here you've got the sun, our Oort cloud, which kind of defines the outer edge of our solar system. And here is Proxima Centauri. Now, this star is what we call a red dwarf star. These are the smallest, dimmest, and most common type of main sequence stars in our galaxy. So much smaller and cooler than our own sun. And being so common and being that they have a very long lifespan, red dwarf star does the sun, meaning it is in the habitable zone of Proxima Centauri, that really amazing Goldilocks zone where liquid water could exist on the surface. Now, given that Proxima Centauri is a red dwarf star, it's probably cooler there significantly than it is on Earth, but still in that habitable zone. And so astronomers and scientists have been very excited about this possibility. But a new research study out of CU Boulder, so just here locally, changes what we know about red dwarf stars and the chances of life developing on planets that surround them. So a team of scientists led by my friend, Dr. Meredith McGregor, who is a professor at CU Boulder, observes Proxima Centauri for 40 hours over the course of several months using 9 different telescopes. This is truly incredible to get that much telescope time. And this allowed them to observe the star in multiple wavelengths. So they were using telescopes on Earth, like the Atacama Large Millimeter Array, which looks at radio wavelengths, and in space, like the Hubble Space Telescope and TESS, which is NASA's Transiting Exoplanet Survey satellite. And so this gave them a really amazing span of coverage, not only in time, but in multiple wavelengths. And during that period, they witnessed what might be one of the largest stellar flares ever observed. Proxima Centauri went from normal brightness, so you imagine that kind of brightness over time light curve Kachin showed us for those black holes. We can do that for stars as well. And it got then 14,000 times brighter in ultraviolet light over a period of 7 seconds. So truly one of the strongest stellar flares ever observed. And this was observed by 5 of the 9 telescopes that the team was using at the time. And so the first time we had multi-wavelength coverage of a flare like this. Now, we think of light as visible light, or the light that we see with our eyes. And this flare didn't produce a lot of visible light, but it did produce a lot of radiation in ultraviolet. So you can think about radiation as what actually gives us a sunburn here on Earth. And also radio wavelengths, and what we call millimeter wavelengths. It describes the wavelength of the light. And so by observing it in this radio wavelength, they actually were able to determine what might have caused this flare. So stars are a really complex magnet. So we can think of magnets like bar magnets, pretty simple. There's a north and there's a south. But as stars rotate, fluid is moving around, these magnetic fields in stars can get tangled. And they can also twist and then kind of snap. And they think that's what happened here, is this twisting of the magnetic field, and that snap created an explosive consequence. And so this flare, we have these on our sun as well, but this was 100 times stronger than anything we have ever observed on our sun. And this is much more violent than we expected from red dwarf stars. So not sounding so great for life. So this was an artist's conception that was done of that flare on Proxima Centauri. You can see the planet Proxima Centauri B there on the right. And so flares like this, as you can imagine, are not really great news for any life forms on any planets orbiting Proxima Centauri. Over time, with repeated flares, that type of energy could strip away a planet's atmosphere and even expose any life forms that might exist there. We don't know if there are life forms there, to some really deadly forms of radiation, or at least deadly to life forms as we know them here on Earth. And so if there is a life form on Proxima Centauri, it would probably look pretty different than anything we have here on Earth. And a human being on that planet would be having a pretty bad time. But what's even more incredible is that the team of scientists found evidence that this isn't a unique occurrence for Proxima Centauri. In addition to this, what they call big boom, or this huge flare in May of 2019, the researchers recorded several other flares during their 40 hours they spent watching the star. And so the planets around Proxima Centauri probably aren't getting hit by something like this once in a century, but at least once a day, if not several times a day. And that would be an incredibly difficult environment to have an atmosphere and create an environment for life as we know it. Now, what's exciting is they've pioneered now a new technique looking across multiple wavelengths, learning more about these types of flares, especially in the radio waves. This was really revolutionary. And they hope to move forward and study even more stars with this same method and to learn more about what causes these solar flares, or these stellar flares, I should say. And maybe there's even, they say, some physics they might not have ever thought of before that they can find. So bad news for life on Proxima Centauri IB, but a pretty incredible discovery right here up in Boulder. Now, I do want to take us into the solar system. This is my typical realm for 60 Minutes in Space, a little closer to home, although not very close to home with New Horizons. This mission is near and dear to my heart, as it visited our favorite dwarf planet, Pluto, has flown by a Kuiper Belt object, and it's really been breaking records since launch, with being the fastest human-made object ever launched into space, performed the furthest flyaway ever in space exploration history, and now it's joined an elite class of just a few spacecraft. On April 17th, New Horizons crossed 50 astronomical units away from the sun. So that is 50 times the distance between the Earth and the sun, or about 5 billion miles away from the sun, which is incredible. There have only been 5 spacecraft that have ever reached that distance. So in this graphic here, you can see the trajectory of New Horizons, which is in red. Arrokoth there marked is that Kuiper Belt object that New Horizons flew by in 2019. It looked kind of like a snowman, or BB-8 if you were a Star Wars fan. And it has continued going out to the outer edges of our Kuiper Belt. And of the other spacecraft that have reached that distance, we have Voyager 1 and Voyager 2, which of course are now in interstellar space, and then their predecessors, Pioneer 10 and 11. So this is truly a feat of human achievement to be able to say we have spacecraft out that far. To give you a perspective of how far away this is, when we think about communication, we use radio waves, and those travel at the speed of light. And right now, one-way communication, so from Earth to New Horizons, takes 7 hours. And then to hear that the command was received and instructions were received, the spacecraft takes another 7 hours to get that signal back. So really quite a distance away. And the scientists did something pretty cool to commemorate this milestone. They turned their cameras to where Voyager 1 is located. And you can see where it would be located in that little yellow circle there. And never before has a spacecraft in the Kuiper Belt object photographed the location of an even more distant spacecraft, which of course is in interstellar space. So really amazing. Now, Voyager 1 was too faint to be seen directly in this image, about 1 trillion times too faint to be seen, but we do know its location exactly thanks to NASA's radio tracking. And so at this point, Voyager 1 is 152 astronomical units away from the sun, so more than 14 billion miles away and more than 11 billion miles away from New Horizons. So can't see it in this image. We can see several stars there, some faint galaxies, but we can mark that location. Now, New Horizons will join the Voyager spacecrafts in interstellar space in 2040, so it's still got a ways to go. And this isn't the end of the mission for New Horizons. Of course, its primary mission was that flyby of Pluto and its moons, but they are still, scientists here on Earth are still using giant telescopes like the Subaru telescope to scan the skies for maybe another object that might be in New Horizons' path out there in the Kuiper Belt object. It's a long shot, but we'll see if that might happen. And New Horizons itself, the spacecraft remains healthy. It's collecting data, so it's very useful on the space environment out there in the Kuiper Belt, on solar wind, and as well as looking back at Uranus and Neptune as well. And they're hoping to continue these scientific discoveries and data collection. They're actually going to upgrade New Horizons by sending a software update this summer. And we'll see what we can get. New Horizons still has a decent lifespan to go. Its nuclear power should power it through at least the end of the 2030s. So here's hoping for more from New Horizons. Now, we will get much, much closer to home here with Perseverance and its new friend Ingenuity. It's a little stowaway. I think this is fun. Perseverance has joined the rover tradition of taking a selfie of itself and Ingenuity. You can see about 13 feet away from the rover there. This was taken earlier this month on April 6th, which was the 46th Sol or Martian day of the mission. Now, taking a selfie on Mars isn't as easy as it is here on Earth to put out your hand and click. They did use the robotic arm to get a camera far enough away for this, but this is actually a composite of 62 images taken by two different imagers, Watson and Sherlock, and that are at the end of that robotic arm and were stitched together here on Earth. And this was taken just a couple days before the historic first flight of Ingenuity. So on April 19th, NASA made history. We have officially flown the first aircraft ever to make a powered controlled flight on another planet, which is just an amazing feat with it. Now, this solar-powered helicopter became airborne on 3:34 a.m. Eastern Daylight Time on the 19th. So it was a time the Ingenuity team determined could have the ultimate energy and flight conditions to make sure this was a success. Now, this first test flight was pretty simple. It flew up 10 feet, hovered for about 30 seconds, and then touched back down. So a total flight time of only 39.1 seconds. But it did snap some images. You can see an image there that it snapped of itself, of its shadow on the ground, as well as some rover tracks. Now, this flight is autonomous. Remember, we still have a communication delay, even to Mars, even though this is much closer to New Horizons. It's several minutes. So we can't fly Ingenuity with a joystick or fly it live. And so this was piloted by onboard guidance and navigation, and the control systems that were running algorithms that were pre-programmed by the team at the Jet Propulsion Laboratory. So we were not quite sure how that would go, but it was very successful. And just a reminder that this is a huge engineering feat to be able to do this. And Ingenuity truly is just an engineering test, setting us up for future missions. But Mars has a third of the gravity of Earth, and the air pressure is only 1% of what it is on Earth, meaning there's relatively few air molecules which Ingenuity's two 4-foot wide rotor blades could interact with to achieve that flight. Which so just fantastic. Now, it has since completed 2 more flights. We have a video here from the Perseverance rover. You can see a little Ingenuity down there in the corner spinning up. Now, Perseverance serves 2 purposes for Ingenuity. It is a communications relay between Earth and the helicopter. Oops, and maybe this will play here. There we go. But it also chronicles the flights of Ingenuity with its cameras. So there it goes flying up. And so this video was taken by Perseverance's Mastcam Z, which is a high resolution color imager on the rover and this is Ingenuity's 3rd flight. And it continued to set records during this flight. So that helicopter took off at 4:31 on the 25th, so just this last Sunday. You saw it reach 16 feet above the ground, which is the same height as its 2nd flight. And then it zipped downrange about 164 feet, which is just over half the length of a football field. And then we'll see it come back into frame here pretty soon as it came back to its landing site. There it goes, and set itself down. So it traveled just over 330 feet total, over 80 seconds for the flight. Now, this helicopter is not moving particularly fast. It reached a top speed of 6.6 feet per second, or about 4 miles an hour, so a brisk walk. But it really is demonstrating those capabilities for future missions on Mars. And they continued to try and push the limits of ingenuity, including using its camera. So this was a color image taken from the second flight of Ingenuity. This is one of the first ever color images taken by Ingenuity. The spacecraft itself, the helicopter, has two different cameras on it, a black and white navigation camera and this color camera. And where the challenge becomes is that there's limited processing power. This is a very little helicopter, and the computer power is being shared between the navigation systems that are doing the autonomous flight and these camera processing, because the black and white navigation camera is actually analyzing the surface features underneath it. So as this helicopter flies greater and greater distances, more images are taken. And if Ingenuity flies too fast, the flight algorithm can't track those surface features. So they want to see where that point is. Now, this image just came down today. This is hot off the presses from Ingenuity. They actually caught a picture of the landing site of Perseverance, as well as Perseverance itself. There you go, it's a little closer view of that rover. And at the time this image was taken, the helicopter was 16 feet above the ground, so that same flight height we were talking about earlier, and it was about 280 feet from the rover. So not a bad image. It's really pretty spectacular for a moving helicopter to take this image. Now, Ingenuity will have at least 2 more flights. Again, just being an engineering test, this is not a long duration mission. And they're going to continue to try and push Ingenuity's capabilities with every flight. Then Perseverance, the rover, is going to focus on its own mission, which is searching for signs of past life in Jezero crater. So we are looking forward to finding out more from those future flights of Ingenuity and as Perseverance as it starts its own mission. But so far already a really amazing success of a mission with some pretty incredible engineering feats that have been tackled. Now, on a sad note of today, Apollo 11 astronaut Michael Collins passed away. Now, he is one of 3 astronauts that were on the first mission to land on the moon, although he was the pilot of the command module and never actually landed on the surface of the moon. He was sometimes referred to as the loneliest astronaut in history. But he was a tireless promoter of space. He always said exploration is not a choice, really, it's an imperative. He has had such an incredible life beyond that mission, beyond that hard mission of knowing that you are going to be the one that travels all the way to the moon and never gets to land. And if something goes wrong, he had to be the one to tell the families of Neil Armstrong and Buzz Aldrin. But afterwards, he went on an amazing career promoting space exploration, leading the National Air and Space Museum, gaining wide exposure for the work of all of the people who helped push the US into really greatness in space exploration and aviation. So with today, we want to remember one of the pioneers of space exploration. Now, I don't want to end on a down note. Sorry, there's a down note there. So let's look forward a bit. 3 years. It is officially April, so that means the next total solar eclipse is only 3 years away, at least one here in the United States. Now, if you saw the total solar eclipse in 2017, you know how amazing these solar eclipses are, and that it's absolutely worth seeing totality. Some of us really love them a lot and tattooed a solar eclipse on our wrist. So we won't be able to see totality here in Denver. Totality is, of course, that place where the moon is completely covering the sun. You see the corona around it, see some just amazing features. But here in Denver, you can see this line here. We'll see a nice bite out of the sun, but it is well worth the trip to get along what we call the path of totality. This is where you will see the total solar eclipse, the moon blocking out the disk of the sun. Now, for those of you that don't want to travel, never fear. With a little bit more patience, you can see a total solar eclipse here in Denver. You're just going to have to hold out till 2045, but you will see 7 minutes of totality. So hang on and make those real estate plans accordingly. And with that, I think we can turn it over to Q&A.
All right. Thank you so much, Kachun and Naomi, for those wonderful presentations. And we have some questions about Mars for you, Naomi.
Okay.
Is Ingenuity having any problems with dust on its solar panels?
Not yet. It was delayed as we're trying to power up the computer. But one of the first tests that they did was to make sure there was power there. It has only been on the surface for a few days. It was stowed underneath Perseverance in a nice apparatus made by local engineers here at Lockheed Martin. So typically we start seeing problems with solar panels with rovers over longer periods of time than this. So far so good. And for a short duration mission, we don't expect any problems.
Awesome. And Kachun, people were aware of the black hole in the center of our galaxy, but didn't realize there were a lot more. How many black holes are there in our galaxy?
That's actually a really good question, and astronomers don't actually really know. I'm not a expert on observational, black holes astronomy, especially for smaller mass ones, which are the ones that actually are the result of massive stars dying. But I think surveys have only, people have looked for them, and we only know of on the order of a few hundred, if I remember right. But there are estimates that based on stellar evolution and just modeling of how the galaxy evolves over time, there should be probably millions, if not tens of millions, of these black holes out there. And of course, many of them were probably not in binary systems or multiple star systems, or perhaps many of them have evolved to the point where the other star or other stars in those multiple star systems have also died. So they've either been ejected in orbital maneuvers, or they've been swallowed by the black hole. So there is still a lot to be learned about exactly, how black holes evolve over time in our galaxy. But there probably are lots of black holes out there, but most of them we can't observe with our current telescope technology.
Interesting, fascinating. And are we still in touch with any of our other spacecraft that are out of? Are we still talking to Pioneer and Voyager?
We're still talking to Voyager. In fact, actually, we just got back into contact with Voyager 2 in the last several months. The problem is, as spacecraft get further and further away, any signals we send or they send back dissipate. This is the same reason stars are fainter further away than they are closer to us. The same is true of radio signals. So we need a really big radio dish to be able to transmit signals that distance, and then also to be able to listen for very faint signals coming back. And Voyager 2, we had lost contact with because of the way it had flown around Neptune and done the flyby of Neptune's moon Triton. It actually put it on a more southern trajectory. And we didn't have as many radio dishes in the southern hemisphere. And they actually just completed an upgrade to one, and I just blanked on the location, I apologize, that allowed us to get back in contact. So we are getting radio pings back and forth from Voyager 1 and 2. Pioneer, I do not believe that we are.
Now the Pioneers have, their batteries are long dead.
Yeah.
And the other problem with contacting Voyager 2 is that its battery strength has also been decreasing. So the amount of power that it can put into sending out a signal decreases with every year.
Yeah.
Now, this is a very important question. If not for those solar flares, what would the temperature be like? What would the climate be like on that planet around Proxima Centauri?
Oh, still very chilly compared to Earth. This would not be your tropical beach planet by any stretch. And there's an interesting question too, that being on orbiting a smaller star, there's likely something we call tidal locking. So the same thing we see with our moon, we only see one face. It's thought that planets around these red dwarf stars might be tidally locked. So depends on whether you're on the daytime side or the nighttime side, but chilly compared to Earth, significantly chillier.
All right, so we'll keep looking for a better planet out there to vacation to.
Yes.
And Kachun, black holes, do they just stay there forever or do they eventually die?
Well, black holes, if Stephen Hawking's idea of Hawking radiation is correct, black holes will eventually evaporate, but they will take an extraordinarily long time to do that. I mean, much longer than the age of the universe now for even stellar mass black holes. We're talking, hundreds of trillions of years. And for much smaller black holes, the evaporation rate actually increases. I would have to look up to see exactly how long for the various black holes that we've talked about. But otherwise, black holes in our universe are like any other object with mass. Every object in the universe with mass has some gravitational force. So even you and I and every object in the room around you has a small amount of gravity, but since gravity is a relatively weak force, we don't feel it. And so, if a black hole is out there in space, it will move according to gravity, and objects will move around it according to the gravitational pulls of everything. And so if you're not headed straight towards a black hole, there's no reason why you and the black hole can't be in coexistence for eternity, as long as your trajectories don't change. And so so one misconception I like to dispel every time I talk about black holes is that you can't think of them as like vacuum cleaners in space that suck everything up. Oftentimes things can peacefully orbit black holes forever if there's nothing to disturb them and cause them to have a trajectory that allows them to intersect with the black hole.
All right, good. Whew. Since you just told us about those millions of black holes, I'm glad to hear that. Here's a very general question. How did the planets get all their different colors?
That is a very general question. So the planets have different colors, partially because of what they're made of. So Mars, which I have our Mars diorama behind us, Mitch has a picture of Mars there, has a very red color because of iron oxide in the regolith, or the dirt, that reflects red light. If you look at planets on further out in our solar system, the gas and the ice giants like Jupiter, Saturn, Uranus, Neptune, we look at what the atmosphere is made of. That can, and the way the light from the sun interacts with it gives those different colors. So you have things like hydrogen, helium, methane, all giving those different colors. And then Pluto is kind of orangish because it's got some methane there on the surface. So the colors tells us a lot about what it's made up of and what's going on. So on Earth, you see those beautiful blues from water, green from trees, many different colors all throughout our planet based on different rocks and things that are on the surface too.
All right, thank you. And then Kachun, what is the, people are wondering about the relationship between the star orbiting a black hole. Like, is there a transfer of mass? Is that a stable rotation that'll last forever, or?
Yeah, I mean that if you have a binary system, and if the black hole and the companion star are close enough, what can happen is that you can define what's called a Roche lobe, and that's the Roche lobe is basically the region in which the star's gravity dominates, and so any gas within that Roche lobe will stay with the star. But if the star, oftentimes stars can go through contractions or pulsations, and so their diameters actually change, and what that means is that part of the star's outer envelope can actually go beyond the Roche lobe. And so if a black hole is orbiting close enough for that Roche lobe overflow to go into the black hole, then that's where you have a transfer of mass into a black hole. And so part of the complication is that as stars evolve, things don't stay constant. So they don't, especially massive stars pump out winds. Towards the end of their lives, all stars, even our sun, can go through variable stages where their diameter or the radius changes and can contract and expand over time. And then we think of on the order about half the stars out there are in binary systems, and then depending on the surveys you look at, another 10 to 20, 15% or in triple systems or even greater numbers of stars within a single system. And oftentimes when you look at more massive stars, they are also in, they tend to be in larger multiple systems than just binary systems. And so that means the evolution of these systems can be extraordinarily complicated. And so people can obviously model them, but trying to find examples of them in real life that we can observe have been extraordinarily difficult, just because these black hole systems are not as common, as other types of multiple star systems. So, how these systems evolve over time is still a really interesting problem for astronomers. And obviously, the binary systems that we can look at, they seem to be somewhat stable while we're looking at them, but they will undoubtedly change and evolve over time as the other star evolves.
All right. So we need more time and more telescopes. And Naomi, a couple more questions about Ingenuity. How does it navigate? How does it not land on rocks and fall over? How does it work? And also, will it ever come back to Earth?
So Ingenuity itself has a really amazing navigation system in it, that it is taking images as it's flying of the ground beneath it, and it's using that to help navigate some of the more perilous landing locations. But as of now, Ingenuity really it's flown up and down, it's flown up, over, back, and down. So where it's starting and ending is the same. There are programs uploaded ahead of time via Perseverance from back here on Earth. And Perseverance, of course, has an amazing set of cameras that can look around and really tell us what it is, what its terrain is like. And they've picked a pretty flat area. We are not far from the landing area, which needed to be pretty flat and open for Perseverance to safely land, which had its own really cool navigation system with its sky crane for landing. So we're pushing the boundaries there, which is incredible. So.
And will it ever come back to Earth?
Ingenuity will not come back to Earth, but Perseverance is part of the first ever Mars sample return mission. So the plan is for Perseverance to collect samples of Mars, leave them in a strategic location, and a still to be planned mission that'll be a joint mission between NASA and the European Space Agency will go and pick up samples. But our little helicopter friend will forever remain on Mars along with the rest of the robots we have sent up there.
All right. Well, that is about all the time that we have. Hopefully, I'm going to put in the chat a link. Hopefully you can all join us next month to hear what new things were discovered in space over the month. And do we have any final thoughts from our space experts? No, you spent hours giving all of your thoughts. Well, thank you so much, everyone, for joining us. This was really fun. I hope you all have a wonderful evening and, look up at the sky and think about all our friends out there exploring. Thanks so much, everyone.
Thanks, everyone.
Have a great night.